going to start now with circular motion. And I don't want you to think that this is a brand new topic coming out of nowhere. This topic will look just like what we did last week and the week before. We're just adding some small variations. So we're going to be applying Newton's laws. You've seen some of this before. We're going to introduce it a little more deeply. So I don't want you to feel like we're completely changing direction. All of what you've learned so far will become useful for today's lecture and the rest of the next 3 weeks. So here's what we're after today. Again, you've seen this before in many different cases. We're applying Newton's law of force and motion to describe and analyze the dynamics of objects in, remember, uniform circular motion. So we're going to start with uniform circular motion, which we'll define very clearly. You've heard it before, but we'll do it again. We can actually study, and we will over the next several lectures, motion that is non-uniform. So motion where there's circular motion, but it has an acceleration. It speeds up or slows up. And what we're going to do, this is the part that should look like almost review, is we're going to use this idea of free body diagrams to show you that in uniform circular motion, we can understand it the same way we understood kind of kinetic, static, equilibrium problems. Okay? So all of those things that we've already studied, you're going to see them crop up again, just now applied to a different topic. But now we're going to go back. Before we do that, let's do our first question. This should look horrifyingly familiar. So take a minute. You can try this with people around you. You can double check your understanding of the problem. I swing this ball over my head. So remember, it's above my head. Spinning it around. You're looking down on this ball. And I'm just swinging it around in uniform circular motion. And then that string, the tether, is just snapped at the point that it's shown. So right where that point is, the ball gets kind of disconnected from the string. And the question is, be careful of the question, because there were several of these when we were studying this before. Which best represents the force vector immediately after that tether snaps? Okay? So again, this should be reviewed, but it's not unusual for people to miss this one. Okay, about 10 seconds. So I have about 100 responses, 6 seconds. Okay, 2, 1, I'm going to stop. Okay, so here's what I got. 72% said D, none of the above. And the only other one that had really any answers is A, 21%. Okay? So basically we got a majority that said none of the above. We still have about 20% that said A. What do we know about, let's start even simpler. In uniform circular motion, if I cut the string, right at that point, which direction will the velocity be? Straight up, right? The velocity of the ball is always what? Tangent to the circle in uniform circular motion. Which direction is the acceleration in uniform circular motion? Always towards the center. So in this problem, that would be to the left. Okay, so you remember this. Now, what is the only force acting on that ball once it gets released from the string?
Gravity.
Gravity. Which way is gravity pointing in this picture? Down, into the board, right? So when you say down, I think you actually meant into the plane of the cage, right? So gravity is going to pull the ball down from this position over my head, and it's just going to fly and drop to the ground, okay? So what's the answer then? Which of these is the force vector immediately after the tether snaps? It's none of these. It's into the plane, which is none of the ones shown here. That's gravity pulling them, okay? So if you missed this one, come back to it. We're going to start to treat this a little more carefully, but you've probably seen this demo. I actually did this demo last week for 1st through 5th graders. I did it the 2 weeks before that for kindergartners. They love this one. It's really simple. They've all seen these before. You probably have not in a while. Do you ever jump in those pits where you can like dig for change? I mean, people used to like look for jewelry and stuff on the bottom. So these are pit balls, and this is a bucket full of them. And the demo is really simple, but it turns out the physics is actually pretty tough, and we have to be careful, and we're going to talk about it today. So you probably all know the answer. If I spin this over my head, what's going to happen? I get 2 different answers. What are the 2 answers I get? They're going to fall, or they're going to stay. Right? This is just like kindergarten. They do the same thing. Fall, stay, and they fight about it. Watch what happens. Okay? Really? happens. I can basically choose what happens. Let me pick up a few of these, we'll do it again. This is the part where the kindergartners are really great. They have this natural instinct to like charge towards the stage and pick up all the balls. I don't understand why, but that's what the natural inclination. So let's do it again. Now I don't have quite as many, but it should be the same. Now, is it going to fall out or stay? Who knows? Yeah. Okay, good. I had a really good question. She said, how fast are you going to go? It depends on how fast, the speed that I'm moving through this circle. Why does it depend on that? What is the direction of the force or the acceleration in this problem? When I have uniform circular motion, what's the direction of the acceleration? Always towards the center. Has anybody ever heard of centrifugal force? Yeah. Okay. I think I already brought this one up. You should forget it. Okay? It's a fake force. So what people used to say, and actually if you go into a chemistry lab, you'll mix chemicals in a centrifuge. What they say is that there's an apparent force on these balls. When I move it through the top of this circle, there's a force that's pushing it up to keep it into the bucket. And they call this the centrifugal force. That's garbage. It's complete bogus garbage. Okay? What is the acceleration in uniform circular motion? Always towards the center. So which way is the force that's holding the balls in that uniform circle? Towards the center. It has to be, when I lift up the bucket to the top, the force has to be down on the balls to keep them in the bucket. Okay? We're going to come back to this. By the end of this lecture, I hope you see why this is true. But it's not obvious, right? If you're not careful, it's not so clear. So we'll come back to it. We're going to treat this really carefully. So this slide again, this is basically Newton's laws. Again, you've seen all of this many, many times. You've even been somewhat tested on it. We tested this on exam 1 a little bit. But basically, the things we'll use are the same things we've been using. Newton's second and third law. Remember, Newton's second law is acting on each body, and it just says the sum of forces is m times acceleration. And then Newton's third law allows us to draw action-reaction pairs. So for every force, there's an equal and opposite reaction force. Okay? We're just going to use these in this new way of thinking of physics. We're going to do a lot of circular and rotation motion over the next 2 weeks. So here's this example that I did. Again, a top view of this tether ball spinning around in a circle. There must be something, some object, some contact force that's supplying the force necessary to keep the object moving in a circle. Right? In the case of the tether ball, I think we all knew this. We played with this quite a bit. The tension in the string is what supplies the force toward the center, and that keeps the ball moving in the circle. So again, in this circle that I've shown here, it's going in this direction, so clockwise. At this point, this lower ball, what's the direction of the velocity? Always the direction of the velocity vector, tangent to the circle, right? So at that point, there's a tangent going down, and if I go to the next point along the circle, what happens? My vector turns, and it turns, and it turns. Every point on the circle, the vector is changing direction. That requires an acceleration in the system. So we've solved this really carefully pre-exam 1, but we're going to go work through this again because there's a lot of challenging intuition that we have to get. So now I think of a side view. Here's a very simple side view of this. Again, I can show you. We've been thinking about the top view. What I'm doing is this, and I want you to think about the side view when it stops here. Okay, so I'm freezing the frame right here, and I'm asking you to draw a free body diagram. And that's what I've shown in that picture. So if I assume the ball is a point, I basically have weight. I have something like, if I'm doing this on a table, which is a similar example, this thing is spinning around. There's a normal force, right? If I'm doing it in air, there's just weight. But if I have it on a table, there's a normal force of the table on the ball. And then there's a tension that pulls it towards the center of the circle. Okay? So this should look pretty familiar. It's just a free body diagram of a ball kind of rolling around on a table. And we know, again, vectors have magnitude and direction, so we know that the vector of acceleration in this problem is the quantity v squared over r. This was the centripetal acceleration, magnitude, but it's always toward the center. Okay? So this again, this should be review at this point. We've even done this quite a long time ago. Now, that implies immediately, if we know there's an acceleration towards the center, we know that there's a net force always pulling toward the center. So in this case, the force that's doing that is the tension. It's the tension of the rope on the ball, and it's pulling it in the direction of mass times acceleration. So we know the acceleration vector. And so we can actually get the magnitude of the force, which is mv squared over r, and we can get its direction toward the center. Okay? So this should look like review. In this particular problem, we know that in order to have uniform circular motion, everybody in this room from some previous life knew that the acceleration is towards the center. Everybody remembers this. Acceleration is always towards the center. What does that imply about the force in this problem? In any problem where there's uniform circular motion, which direction is the net force? Always towards the center. So if I show you any situation and I say, this is approximately uniform circular motion, you have to look for that force that's keeping it in uniform circular motion. There has to be a force pulling towards the center. So these things are often camouflaged. We're going to hide lots of different situations where you have to dig out that fact that in uniform circular motion, I always have a force towards the middle. And again, you understand it when there's a rope there, but if I show you a different situation, you may not believe me. Now here's a really important question. Is this system in equilibrium? Why? Why is it not? I see people saying no. Why not? Why? She says the velocity vector, so while the magnitude of the vector doesn't change, the direction of that vector is constantly changing. That means that there's an acceleration in the problem, and we know that if there's an acceleration, it's not in equilibrium. So this one's tricky because we say that the speed, the magnitude of the velocity, the speed, stays constant. And if you remember, in equilibrium, the vector velocity stays constant, or zero. So we could call it equilibrium. This one, only the speed stays constant, but the direction of that vector changes. And so we say that this is not in equilibrium. It's an acceleration. And if you go back to these notes from kind of the second or third week, we derived this. If you remember, we summed the vector at t plus delta t minus the vector at t, and we saw that we could draw the acceleration towards the center. So we've seen all of this before. We have to be careful. This is not an equilibrium system, even though the speed is zero. So here's how this works, and we're going to show lots of examples, lots of conceptual examples. So for uniform circular motion, a force whose magnitude is constant, but whose direction is always pointed from the object to the center of rotation, is needed to provide that centripetal acceleration. Little kids, again, I was telling this to kindergarten and fifth graders, and one of them raised their hand and said, is that the same thing of the force that's holding the moon to stay in a circle around the Earth? This was a bright little kid, right? He was probably maybe 8. And what's the answer? What's the force holding the moon in uniform circular motion around the Earth? Gravity, right? The gravity of Earth on the moon pulls toward the center, and it keeps it in uniform circular motion. It has to be somewhere in a circular motion problem, there has to be a force pulling towards the center. Here are the 3 requisites. So when we think of uniform circular motion, these are the 3 ways to kind of double check that this is going on. And one of these notations we are just introducing. But the first thing we know is that a particle must be moving at a constant speed around a radius fixed at r, right? If I am changing the radius as I go, that's a really weird problem, right? If I have a radius of this rope, I can do this actually. We'll actually solve problems like this, but I can spin this around and I can let it get longer and longer. That's a really complicated problem. Uniform circular motion assumes that it's always fixed at a radius r, so it's just a circle. The other thing is that there has to be a centripetal acceleration. Again, you remember this, you know this, you've done some problems with this. And the acceleration has a magnitude v squared over r, always toward the center. And then the last piece, which we're going to introduce some new kind of characters, new algebraic characters to understand, is there must always be a net force equal to m omega squared r pointing towards the center. So for now, just note this down. We're going to spend the next 10 minutes understanding all of this information embedded here. Mass you know, the radius you know. Omega is going to be called the angular speed, and we're going to define that in a second. So omega is the angular speed, and in this quantity, the force is squared of the angular speed. Okay? So before we go any more into these concepts, let's do some kind of mathematical definitions. And I want to draw some things on the board so that you really get this, because there's a lot of information packed onto this slide. Okay? So this is a good slide to have when you're doing these problems, because it will help you kind of recall all of these pieces. But before we look at this, let me draw something really simple first that I think you'll all remember and understand. If I think of uniform circular motion or circular motion on an xy plane, so mathematically, what angle do we call the x-axis in degrees? 0, right? So everybody remembers this. I'll write this as 0 degrees. And which way does this degree increase on this circle? Counterclockwise, right? So if I go up to here, what's the angle? 90. Right here. And draw this way, this way. This is 180. This is 270. Okay. There's even a problem on your first exam that basically asks this. Right? If I have a vector with negative x and y components, it must be in this kind of part of the diagram. Okay? So if we think about this, now we can ask, how do we think about rotation in these coordinate systems? We're going to define some new pieces. So let's say I have a particle that's right here at a radius, I'll call it r. Just to keep it simple, right? And this object is going to be rotating. So again, I'm going to show you so you get really clear on this. This object is this ball, and it's rotating in what we're going to call the positive direction. The positive direction is the direction that the angle's increasing, just like we said, around this circle. So it goes from 0 to 90 to 180 to 270. Okay? So our convention, this is positive. What's negative? Just the reverse. Okay? That's a convention. So this graph that I'm showing here will define that mathematical convention. So let's say we can start really simple and say this is at T1. I take a snapshot of this object, and I look at its radius, and I look at the angle that it is from the x-axis. So I'm going to define this as theta initial. And I can call this 1 or initial as well. So that's my initial time. I take a snapshot, and I look at its angle. Now it's increasing, it's going around this circle, so I'm going to take another snapshot at a short time later. The radius is the same. I now have T final, right? I go from T initial to T final. And I now have an angle that is, we'll call it theta final. I'm going to move this R. Okay? So you can kind of guess. That first angle looks like it's about 20 degrees. The second angle looks like it's about 50 degrees. Right? So I went from 20 degrees to 50 degrees in a time delta t. Okay? So the time that we've traveled, just like we've always defined it, is t final minus t initial. Right? This should look familiar, like kinematics. The angle that we've traveled, delta theta, is equal to theta final minus theta initial. Does that make sense? So we just moved, this circle has moved, this object has basically moved in a circle at some angular velocity. We're going to define in a second. Okay, so we moved delta theta in a time delta t. So we can now write down, just like we did, just 1D kinematics. We're going to define this new one-dimensional parameter. This is just like 1D motion. We had velocity defined as the change in displacement over the change in time. Now there's a rate of change of theta, and it comes out very simply. We've defined it as omega. We saw it in this previous this slide, we'll see it more and more. It's the change in angle as a function of time, right? So in delta t. So remember, we can actually go a little bit further in this. So let me write down a few things. So what's the speed in uniform circular motion? What's the speed? Okay, how do we think about it? You actually saw a problem like this, and this one was, I think, on the practice exam, maybe even on the exam. The speed is really simple, right? If I go a distance and I divide it by the time, that gives me the speed of my object going around the circle. So if I write this, I can say that the distance I traveled is the circumference of the circle over the amount of time to get around the circle. Right? It's super simple. If I have to say how many times around the circle do I go, that's basically a number. I know that's divided by the total time it took. Right? So, what's the circumference of a circle? 2 pi r. Just checking. And what we're going to do is label this thing, which is the time to get around one full circle. We're going to call that the period of motion. And we give it a parent capital T. So when you see this is a language that you might not be familiar with. When you see this language of period of motion or period, that's the time it takes to go one full circle. Let me give you another example of a period that we'll work with later that's defined a little bit differently. If I have a pendulum, you've probably heard this in pendulum. One period of motion is the whole way from start to finish, right? I start here, 1 period, 2 periods, 3 periods. So each time I finish that whole range of motion, I'm going to call that a period. In a circle, it means you go the whole way around. Yeah.
So each time you get back to where you started.
Exactly. So in any situation, that's how it's going to be defined. You get back right to where you started. In this case, it's a circle. We're going to work with circles. We'll work with pendula a little bit later. Okay? So far, all of this is good. And now I can define this angular, I'm going to rewrite this angular speed. We have a definition, delta theta over delta t. But I want to write down a more explicit version of it that you can actually solve things from. So here we have two very different quantities. And this is where we're going to get stuck. I think a lot of people get hung up on this as we learn. On one case, we have speed, which is basically I have to travel the whole arc length of a circle, right? And I just ask, what's the circumference divided by the time to get around the period? The angular speed is much different. It's the angle traveled in that full circle, which is what? How many degrees do we travel in a full circle? 360. How many radians? 2 pi. Okay? When we work with these equations, this is probably something you might even remember from high school. You have to be really careful when you're calculating whether you're entering your angles in radians or in degrees. Most of what we'll do will be in radians. So this quantity, omega, is just 2 pi radian over the period t. Okay? What is the one factor that makes these two things different? So the speed is 2 pi r over t. The angular speed is 2 pi over t. What's the one factor that makes it different? The radius. So these things have a relationship. I can write the speed as the angular speed times the radius. Okay? So when we think about what happens, there's a really good situation that I've been asked a lot about in this class and every other class, and you'll see it more, is that when the radius changes, that changes your problem in various ways. It might, if I have the same angular speed, I'm going to travel a much longer arc length. If I have the same speed and I change the radius, I'm going to be traveling a different angular distance. Okay? So those things are related by this radius r. Now there's one more thing I can show you, which is just going to get back to what we said a minute ago, which is how do we relate, what did we say the centripetal acceleration was? Everybody remembers, the magnitude of the centripetal acceleration is v squared over r, right? I can write down the centripetal acceleration using this omega, and then I have a new version of thinking about the acceleration. You probably do it in your head. I'll write it down. So v squared is going to give us an omega squared, r squared over r, or omega squared over r. Okay? So now, if you see what's happening here, let me show you a couple things about this. It seems pretty simple, I think, so far. If you go back to what I said just a few slides ago, I said that there must always be a net force equal to m omega squared r. You see that this is identical to saying mass times acceleration. There's my acceleration, omega squared r. So we're just using this new parameter that is angular speed, which is different than the speed on the outside of the circle. It's the angular speed, but we can use it to quantify the same thing. So now I think I've covered basically everything in this slide, starting from, where did I start all of this mess? I defined a coordinate system, and I said that the angle increases in this direction. That's what we're going to call the positive direction. We'll test this over and over the next couple of weeks. But now, based on that, I can write down all different things. I can talk about the angular position. That just tells me what angle this object is at. I have an angular displacement, which is just the final angle minus the initial. I have an angular velocity, which is just the change in angle over time. I have the period, and the frequency is just 1 over the period, right? So it's the number of circles per unit time that I travel. Angles, again, when you're calculating, they're always going to be measured in radians, and one revolution is 360 degrees, and that's 2 pi radians. So if I go from 0 to 180, what's that in radians? Pi. If I finish, it's 2 pi. If I go one more, add another pi, right? Every half circle is 1 pi, right? It's 1 pi radians. And you'll see problems like that. It might tell you go through 9 pi radians. And so you have to see what that means when you're calculating things, okay? So here's an example. We'll start to work with this. Here's a very common example called the Conical Pendulum. It's a simple movement. All it is I'm now taking this tether ball, and I'm making a circle, but do you see that I'm basically taking a snapshot at one point in time right here, right? This picture that I've drawn on the PowerPoint is just one stop in time, something like this. I take a snapshot. Now what I want to show you is that this is basically just applications of Newton's laws with this new set of parameters, the omega, the acceleration, this relationship, v and omega r, how we equate these things. We can now retreat this whole entire thing. So let's start by just drawing a schematic. If we have this problem, we know that there's a weight pulling down on the ball. This is the problem where there's no table, there's no normal force pushing up this time. It's just hanging from some point, like my hand. And the force that's acting on the ball is the force of tension of the rope acting on this ball. And it's pulling in the direction of that tension. There's some length, there's an angle, and there's a radius. Okay? So if I drew some of the forces acting on this, this isn't the free body diagram, these are kind of components of these different forces. You see that the weight is acting down, but there's an upward force of t cosine theta and an inward force of t sine theta. Which of these forces is producing the centripetal acceleration? Which one's pulling it towards the center of the circle? T sine of theta. So do you see that hidden in this picture? I draw this ball spinning around in a conical pendulum. We know that if there's a uniform circular motion, if I knew nothing about this rope, that I had, or the angle of that rope, I have to have a force pulling inward towards the center of the circle. And in this problem, it's T sine theta. Okay? So when you see uniform circular motion, always remember, I have to have a centripetal acceleration and therefore a force pointing inward towards the center of the circle. So these two forces balance, right? The vertical force is balanced. The ball doesn't go up or down. It doesn't accelerate in that direction. They're balanced. But there's this constant force pulling it towards the center. You see that all we've done here is apply Newton's laws and added the fact that it's kind of a snapshot in a circle. Okay? This force is the one that we now said is causing this acceleration towards the center. So let's see if we understand this. We'll try a couple discussion questions just to see if we can gather this in our minds. Here's an example of the conical pendulum. Same thing I just drew, slightly simpler. There's the length of the rope, theta, and r. It's a ball on the end of the string, and it's going again in this plane through circular motion, which best indicates the direction of this. We've just answered this basically, but just to get the acceleration when it's in this location. So take 30 seconds. Let's see if you actually had your listening caps on. So again, all you're asked, there's a uniform circular motion. In which direction is the acceleration? Okay, 10 more seconds. Okay, I'm going to stop. Oh, this is great. Wow, that's awesome. So 95% of you got the right answer. You were able to translate information from one slide to the other. This is good. So always, when we have uniform circular motion, there's always an acceleration towards the center. That was an easy one. This was a softball. Let's go a little further. Now, which of these is the correct free body diagram? So remember, there's a strict definition of what a free body diagram is and how to draw it. Take a minute and draw the free body diagram of this object moving in circular motion, uniform circular motion in the plane, which is the correct free body diagram for the ball. So take about 30 more seconds. Be careful, because this one is tricky. Okay, 10 seconds. All right, 3, 2, 1. Stop. Okay, this happens every time. So here's what I got. Not quite so unanimous as the last one. Okay. Here's what I have on here. Basically, I have 20% said B, that it's this one. 40%, this is the largest, said C, that it's this one. And then 34% said E, that it was this one. Okay? So basically it's what? A, B, C, and E. B, C, and E. Let's stare at these three. We'll ignore the other two just because they were very much in the minority and ask if we can cancel off any of these. What is the force acting on this ball due to gravity? Weight, down. Can we cancel any of those because of that? No. Okay, good. They tricked us on that one. That was the easy one. Now, what is the force acting on the ball from the rope?
Tension.
It's the tension. And which direction is it? It's toward the pivot point. It's toward that connection. It's up and to the right. So that cancels B, right? That one's missing the force being pulled up and to the right, which is the vector tension. So that leaves us what? C and E? What is this force?
Wait.
Acceleration.
Downward is that?
What is the force?
Acceleration.
What is the object acting on the sphere that pulls it that way? the magic elf, right? The little demon.
That's hella funny.
There's no force acting on the object that you can see. There's no contact force in this problem that is pulling you towards that direction.
That's so interesting.
So this is a common misconception. We know that there has to be a force coming from something that accelerates it towards the center. Wait, where does it come from in this free body diagram? Where does that acceleration come from? We just said it. It's the x component, it's the in-plane component of the tension that provides that acceleration. There's an out-of-plane component that's up that cancels the down, and then there's an inward one that goes in. We just drew this actually here. We took these components visually, we said there's a t cosine theta. I tricked you because in a free body diagram, these are not forces, these are the components, the scalar components of the tension force. Okay? This will nuke you on the exam, right? You have to look. Every force that I draw on a free body diagram, there's a rule that says I have to have a force of A on B. Right?
Yeah.
Okay, now we all know the answer. What's the answer to this one? C. Okay, now, draw this picture. Here's the challenging one. Which is the expression for the ball's speed in this circular motion in terms of G, R, and theta? Right? Sit down. How do you solve a problem? How do you find speed, acceleration, and forces? What relates acceleration and forces? You know it. It's called Newton's laws. So draw this diagram and see if you can apply Newton's law to this situation. I'm going to deliver this question, but you'll take about 2 minutes. So really work through it. The people who draw the best diagrams can write down Newton's laws the most clearly. So start with a really good diagram. Yeah, I know, this happens every year. It's kind of, it's an eye.
Wait, you do this.
Yeah, it's the same answer.
Okay.
Every year it happens, and I want to see if people I get people who will answer A or B and not both. Yeah. There's no difference. Every year I do the same exact trick. And every year I'm just saying, I get people that answer A or B and not both. This happens every year. I love it. So it's the same exact answer. But every year people get that answer, they solve for it, and they get that answer, and they write down A or B. If you see this on an exam, what does it almost immediately tell you? Good. We're learning. Solve the problem. Work through it. Don't worry about what A and B says. Get the answer and then find the answer in the list provided. Right? That's multiple choice. So another 30 seconds. Can you draw this really carefully?
I guess. I just want to see what happens. I was like, I think it's going to be totally different. It's not even the same. Going to others. Plus elimination. You know what to do. We just haven't used it. I mean,
Okay. 2 seconds, 3 seconds. Let's see what we got. Okay, C. I have 74% said that the answer is C. And I think I heard all sorts of funny logic for this. I don't know what this one means. What is the cotangent? It's 1 over the tangent, right? It's sine over cosine, or cosine over sine is the cotangent. You should know this. And there's other, but the primary response I got was C, 75%. But if I ask somebody, since one of those 75%, could you come down and show us how you did it? Anybody? I mean, that's a pretty clear-cut response, right? Okay, let's do it. Here's what I'm going to do. Very simple. I'm going to apply Newton's laws to this problem. One thing I'm going to do in this picture that I want to be really clear about so that it doesn't confuse you is that I have the z-axis, which is up and down. Remember, this is this ball hanging. I'm going to use this other axis rather than x. I'm just going to call it the radial axis. So this is in the direction of the radius of the circle. These are just called circular coordinates. You can see these in math. You've seen them before. I'm certain you may not remember them. Okay? But you can replace basically x with this as much as you want. So I have the radial direction and the z-hat direction. And all I do is apply Newton's laws. Just very meticulous, careful application of Newton's laws. The sum of forces in this radial direction is equal to mass times acceleration. Right? This is just the statement of Newton's second law. I know that the acceleration in uniform circular motion is v squared over r. And I sum up those forces, and we already said it's t sine of theta, and that's the only one acting. Right? There's no other force in the plane acting on this ball. So I get equation 1, which is really simple. T sine theta is just equal to mv squared over r. That's my first piece of information. And I always, you do it every single time, I then have to look at the forces in the other direction. So if I look at the sum of forces in the z direction, is it accelerating up or down? No, it's fixed in the plane. And so the sum of forces is equal to 0. I have t cosine of theta up minus the weight down. That has to be equal to 0. And my algebra just gives me that t cosine theta is equal to the weight. Okay? So far, really simple. I drew a picture, I draw the forces, a free body diagram, I apply Newton's laws, and I decide whether there's an acceleration or not. And then all I'm doing from here is algebra, right? So let me just start one piece at a time so I don't kind of go too fast. This is now just algebra. I'm just going to rearrange. I start with v squared. This is equation 1. I'm solving for v squared. It's r times t times the sine of theta over m. That's just rearranging equation 1. And then when I take the square root, I just get the square root of rt sine theta over m. Now what am I forgetting in this square root? To be strict, mathematically strict, there should be a positive and a negative sign. When you take a square root, there are positive and negative roots. In this physical situation, the negative root isn't physical. Okay? This is how we argue those away. But strictly speaking, mathematically, there should be a plus and minus. If I then take equation 2, I have t cosine theta is equal to weight. It's just equal to mg over the cosine theta. And I'm just going to plug that in to the t in equation 1. Right? So this is just algebraic substitution. And I can finally solve. V is just the square root of mg over cosine theta. That came from t. And then I have the r sine theta over m. And you see immediately that mass cancels out. It's not, you'll find this in general. In pendula, the mass isn't important in finding the speed. It has a sine divided by cosine, which is the tangent, and that's the answer that we were looking for. Okay? So this level of kind of algebraic finesse is what you're going to need to be really efficient at as you go. Okay? So I see some people taking a picture. That's a good idea. Now, let's move on. We're going to find more situations. We have a few more in the next couple minutes. We still have a couple things. Here's one you're going to all be familiar with. Okay? When you're driving on the highway, who's ever gone on an exit ramp in Southern California? Yeah. What's it feel like? Is it flat? No. It's banked. Why do we bank turns? I mean, probably the gearheads in here are like, well, that's because I can go faster, right? It's banked. But why? Why do we bank the turn? This is an important engineering thing. When I grew up, if you go to the East Coast, you almost never see banked exit ramps. This is kind of a recent engineering feat in the last maybe 20 years. So here's what happens when we turn a car. Here's my car, and I'm driving into the page, and I'm turning left around the bend. So imagine, you're in your car, you're pulling into a left turn. I know that if I'm in uniform circular motion, imagine you're just driving around in a circle, a perfect circle at a constant speed. The normal force is the force of the road acting on your car. The weight acts down, and what's holding you on the edge of the circle? It's drawn in this diagram. Is it the force of static friction or kinetic friction? It's static, because in this direction, it's fixing my radius to be a constant value. This is the force of static friction of your tires on the road, or on the road on tires, depending on what you want. So we're going to come back to this. Let's do one more quick question. Here's that banked curve. So a car in a curve. Here's you on the exit ramp, heading straight, turning left, flying around the bend way faster than the little 35-mile-per-hour sign suggests. Here's the center of the circle. You're at some angle theta. The car turns a corner on a banked road at a constant speed v. Which of the diagrams could be the car's free body diagram? What are the forces acting on the car going through this motion? And again, remember these rules about free body diagrams. You should be able to write every force as a force of A on B. Take about a minute.
What would you say you're doing? Just the angle. But see, when you side from the I'm kind of I feel like that's a because it's
Okay, 20 more seconds. Okay, 10 more seconds. See if you can do it. Okay, I'm going to stop here. We'll come back to this next time. I'll see you guys on Wednesday. I'll see you next time. We'll finish this up. We'll see it again.
That's brutal.